today we will look at thermal physics, sometimes called thermodynamics. So we're going to start off by looking at ideal gases. When we look at ideal gases, you're going to see that ratios and proportionality are very useful, so it's well worth getting used to working with ratios and proportionality. First up, what an ideal gas is. It's a theoretical concept, and it's a gas whose molecules occupy negligible space, so the molecules are very, very, very tiny, so that the volume that they occupy is negligible. And they have no interactions among themselves, and they therefore obey the gas laws perfectly. If you have, this is just an example of using direct and inverse proportionality. If x is proportional to y, then x divided by y is equal to a constant. And therefore, if that's true, then you can say x divided by y in situation 1 is equal to x divided by y in situation 2. And so whenever you have a gas law where you have quantities that are directly proportional, you can write it like that. If you have an inversely proportional relationship, so let's say x is proportional to 1 over z, then x multiplied by z is equal to a constant, and therefore xz1 is equal to xz2. First law, Boyle's law. Here we've got a fixed mass of gas. Now you're always going to have a fixed mass of gas for these laws. And if you have a fixed mass of gas that's at a constant temperature, then the pressure is inversely proportional to the volume. So therefore, P is proportional to 1 over V, and then you can write that as I showed before, P1 V1 is equal to P2 V2. If you plot that on a graph, then you've got volume here, pressure on the x-axis, and you get a curve like this. Okay, that's different to an exponential decay graph, and it's different to an inverse square as well, so just bear that in mind. And that's the first graph. Second graph, if you plot v to the minus 1 against p, you get a straight line through the origin, because if pressure is inversely proportional to volume, then it's directly proportional to 1 over volume, which is exactly what that is saying. If you halve the volume, then the pressure will double. That's essentially what it tells you. Charles's law, this is a relationship between volume and temperature. Again, fixed mass of gas. This time the pressure is kept constant, and temperatures must be in Kelvin. So you need to have your temperature absolute, and if you want to convert a degree C temperature into Kelvin, as you know, you add on 273 degrees. Volume is directly proportional to temperature, so V1 over T1 equals V2 over T2. If you triple the temperature, then the volume will triple. Okay, and if you plot V against T, straight line through the origin, and that dotted line there indicating that this is theoretical, because as you approach absolute zero, your gas is at some point going to cease to be a gas. It's going to turn into a liquid at some point, possibly even a solid. So, depending on which gas you're talking about. So therefore that wouldn't apply in that case. If I just, here what I'm going to do is demonstrate the importance of doing a temperature conversion. Let's say T1 is 6 degrees C. That's equal to 279 Kelvin. T2 is 15 degrees C. That's 288 Kelvin. Delta theta is 15 minus 6 if you do it in degrees, and that is actually equal to 288 minus 279. So that is the same thing. If you do a subtraction, it's the same thing in degrees C or Kelvin, because if you add on 273 to both numbers and then take away one of them, you're going to do 273 minus 273, so it will cancel out. But if you do T2 divided by T1, then 15 over 6 is 2.5, and that is not equal to 288 over 279, which is equal to 1. So if you're doing temperature differences, you can work in degrees C or Kelvin, but if you're doing a ratio, as in Charles's law, then you must work in Kelvin, because you'll get different values, and those laws work for absolute temperature. I'll say more about absolute temperature later. Then you have the pressure law. Fixed mass gas, pressure directly proportional to temperature. Again, temperature in absolute, so you can write P1 over T1 is equal to P2 over T2. Add plot P against T, and you get a straight line through the origin again. So if you quadruple the temperature, you will quadruple the pressure. Now, what you can do with those laws is combine them into one, and we call that the ideal gas law. So we combine them all into one relationship, and you're going to see the constant is either nR or nk. Again, temperatures must be in absolute temperatures. So P is proportional to 1 over V, Boyle's law, Charles' law, and the pressure law. So that means that pressure is proportional to T over V, and therefore PV over T is equal to a constant. And using your proportionality constant, which is either nR, now that nR is number of moles multiplied by the molar gas constant, or it can be nk, you've got an uppercase n, number of molecules, Boltzmann constant. So this is the molar gas constant, and this is essentially the molecular gas constant, called the Boltzmann constant. So you can write your relationship as PV equals nRT, or PV equals nKT. Just be careful which one you're working in. Moles and molecules then. So I've just told you that you've got these two ways of working with the ideal gas law, so you'll need to know how to work with moles and molecules. The mole is the amount of substance that contains 6 times 10 to the 23 atoms or molecules of that substance, and the 6 times 10 to the 23 is Avogadro's number, Na. The corresponding mass is the molar mass, so that is the nucleon number in grams. So you take the nucleon number for an element or for a molecule and convert that into grams. So for example, the molar mass of nitrogen gas is N2. Now N has a nucleon number of 14, so 2N is 28 grams. The molecular mass of uranium-235 is 235 grams. And that comes from our periodic table. You're going to have to get used to working with these anyway from Unit 5, because you'll need to know which is the proton number, which is the nucleon number. So the top one, nucleon number, nitrogen 14, uranium-235, and the proton or atomic number 7 and 92. So A is the nucleon number and Z is the proton number. Now, you're not going to have to memorise the periodic table, because they should provide any nucleon numbers that you need to work with in the question. So don't worry about memorising the periodic table. I don't think that would be a problem. There may be some that are useful to know anyway, like such as hydrogen is 1, helium 4, and so on. Just a few. Okay, Brownian motion then. So those are the laws, and we've looked at molecules and moles. Now let's look at some motion and start to look at the motion of molecules and how that changes or how that affects their properties. We'll start with Brownian motion. This is based on the work of a Scottish botanist, Robert Brown. There's a picture of him there, who was alive 1773 to 1758. And the work that he did provided strong evidence for the existence of physical molecules. What he was observing was pollen floating on water. Now pollen, very, very fine particles, very, very small, and he was observing them floating on water. And he noticed that they were in a state of random jerky motion. Now, his experiment was using pollen, but the experiment that you should be prepared to talk about is one that uses smoke particles in air. So the smoke particles are suspended in air. And random jerky motion. Those are, by the way, those are key words that you should refer to in any discussion of random motion. Random jerky. As I say, this is the experiment you should be prepared to talk about. I have got video of it. How well it's going to appear on the big screen, we'll see. But hopefully that'll be helpful. And there are a series of observations that apply to the smoke experiment, and there are conclusions that you can draw from them. So, for example, the smoke particles you can see, and even though you're at such a high magnification in that experiment, you can't actually see the air molecules that are bombarding the smoke particles. So from that you can conclude smoke particles, yeah, they're small, but air molecules are incredibly small, you can't see them, so they're very, very small. Smoke particles, they're continuously moving, this random jerky motion, so therefore the air molecules must be, and so on. So you've got a couple more observations and conclusions, right? One of the things you need to appreciate is that because of this random motion of the air molecules, at any time you'll get a net impact on a net larger impact on one side than on another side, and that's why the smoke particles keep changing direction randomly and suddenly. So this random sudden change in direction causes this jerky motion. So let's have a look at some videos. This is an actual view of smoke particles suspended in air. Okay, so these little bits picking up the light. You've got light shining in, and the smoke particles are reflecting that light, and that allows you to see them. So we are observing the motion of smoke particles, and from our observations of them, we are drawing conclusions about the air that is bombarding the smoke particles. Okay, so there's a very important distinction. Smoke particles are not molecules, it's the molecules that drive the motion of the smoke particles. Over here, this is a visualization of what's happening. This would be a smoke particle here, the yellow blob, and that's getting bombarded by the air molecules, which are much, much smaller, and they're driving this motion of this. And you see this haphazard path that is being carved out by the smoke particle. So that's a visualization of what's happening. It's a visualization because you can't see the air molecules when you look yourself. Okay? So that's Brownian motion. Onto a kinetic theory of gases. So what this does is it attempts to give a theoretical explanation of the gas properties and the gas laws that we just saw based on what's happening at the molecular level. And there are a number of assumptions that are required for kinetic theory, and it wouldn't be worth me just reading them all out, but there's 9 assumptions that you need to know. Okay? So that will, all those, whoops, they're all available, and we've got those on a handout that you can just read through. Okay? So those are all the assumptions, you just need to learn them, there's no two ways about it. Right, so let's see how kinetic theory can explain pressure. And we start off by saying, well, the molecules, they're continuously bombarding the walls of the container that they're in. And the momentum, the component of the momentum that is perpendicular to the container wall is going to be reversed on a collision. So if the gas molecule is going towards the container and then it bounces back, the momentum perpendicular to the wall has been reversed. This bear in mind that they're not all going to be going at right angles to the container wall, but if they're going at an angle, they're going to reflect off, and it's that perpendicular component that we're interested in. That's what is reversed in that case. So that's a demonstration of it there. Okay, so it starts off like this, and it's reversed. So it's got, because the mass hasn't changed, it's just the velocity vector which has changed direction. The force that's required to produce that change in momentum from Newton's second law, and that is provided by the wall, right? So there's a change in momentum, and that force must be provided by the wall. From Newton's third law, if the wall has exerted a force on the molecule, then the molecule must have exerted a force equal and opposite on the wall. Okay? So Newton's second law tells you there's a force involved. Newton's third law tells you about because the force we found from Newton's second law tells us about the molecule, what we're interested in is the container, because we're interested in the pressure exerted by the gas on the container. So Newton's second law, force on the molecule. Newton's third law allows us to say there's a force on the container wall. The total force from all the molecules over the total area of the wall that they're bombarding will give us the pressure. So that's how kinetic theory, by looking at the molecular motion, can explain pressure. Okay? Now, kinetic theory equations. There are equations related to kinetic theory. And we're going to need to define, because this is happening in 3D space, we're going to need to define our dimensions. So we've got x to the horizontal, y is vertical, and z is into the plane here. Containers are 3D, so you've got those. And this is our container here. The length of one side is L. Now, let's consider one molecule. That is, by the way, this derivation is not something you need to know, but the equation at the end of it you will need to know, and I think it's useful to know where equations come from. That's what I'm showing to you. So consider this molecule moving along the z-axis. The force exerted on the molecule is the change in momentum over the time of the collision, delta t. Now the momentum has been reversed, so if it's moving with velocity vx, because it's in the x direction, then it's 2 times the mass times vx, because it had vx towards the wall, and then when it's reversed, it's got vx away from the wall, so therefore it's 2vx, the change in velocity. Now the time between the collisions, in order to look at that, it's travelled towards the wall, it's bounced off, it's going to go back over here, bounce off this wall before it reaches the same wall again. So it will have travelled 2L. And so delta t is 2L divided by the velocity. That's just using S equals ut, constant velocity equation. Because the only thing it's going to interact with, this molecule, is the wall. It's not going to interact with the other molecules. It's one of the assumptions. Okay. So the rate of change of momentum then, we've got delta p, we've got delta t, so we substitute in what we just found. 2mvx over 2l over vx gives us mv squared over l, where v is vx. And if you consider all of n molecules impacting on the wall, and the wall has an area of A, then P is equal to N. N is the number of molecules, times the force that each molecule provides, F, over A. Now, we've just said that F is mvx squared over L. So therefore, N times F is equal to nmvx squared. Now the bar is because not every molecule will have the same velocity. So therefore we take the mean Vx, and we divide it by AL because L comes from there, and the A was provided by the pressure aspect of the equation. Have a range of velocities. Now, AL is equal to the volume of the container. I'm sure you can appreciate that. The area multiplied by L, so AL is the volume of the container. Now, the velocity vectors all add up to the total V squared. So this is the velocity vectors in the x direction, y direction, z direction. And we can assume that there's equal amounts of velocity in each direction. They're moving randomly, that's a reasonable assumption. So therefore, Vx squared bar is going to be equal to V squared bar over 3. So it's just a third of the total amount. Okay, so after all that, you can substitute that into the equation, and then, so this is our substitution here, V squared bar over 3, and AL became the volume. Rearrange that to make it look a bit nicer. PV is equal to a third M V bar squared. Okay, now that is a key equation, so you need to know that equation. So that's the kinetic theory, first kinetic theory equation. Okay, any questions to that? Yes?
Is that in the formula?
No.
It's not.
No.
It's in the handout.
Sorry?
It's in the handout.
Yeah, it's in the handout, but not in the formula books. You'll need to know that one.
Oh, so and also you know that that delta t. I thought that's the time during the collision.
No, that's the time. That delta t was time between collisions. Because it's a rate of change of momentum. Yeah. Okay? Right. Now, from the ideal gas law, we saw that PV is equal to nKT, didn't we? So that was the molecular version of the equation, as opposed to the molar. And therefore, PV is also equal to a third NMV squared bar. So this equation here, that means that this side, the right hand side of the equation, is equal to nKT. And do some rearranging there. What did I do at that stage? Oh yes, that's right, because mv squared bar is equal to 2 times the kinetic energy, the mean kinetic energy. So I've substituted that in there. Okay. Now that's equal to kT. The n's have cancelled out, of course. So therefore we get that the mean kinetic energy is equal to 302 kT, and that's the second kinetic theory equation. That one is given in the formula book. Right. So therefore, the kinetic energy, mean kinetic energy, proportional to the temperature of the gas. And that's absolute temperature. All right. So that was a bit long and drawn out. I know. I don't think I've got any more extended derivations like that. An example explanation of one of the gas laws using kinetic theory. And this is going to be an example of pressure is proportional to temperature. You can do it for volume is proportional to temperature and so on as well. But let's do this one, and then you'll get the idea of how it works. If you've got a fixed mass of gas at constant volume, pressure increases as temperature increases. So, temperature has increased, then the kinetic energy has increased. Therefore, the mean velocity of the molecules has also increased. First, that's the first logical step. Per collision, that means that, by the way, this is the first explanation of this. There are actually two possibilities here. In the first one, if the mean velocity has increased, then the change in momentum has increased, because the change in momentum is equal to the change in the velocity multiplied by the mass. Mass isn't changing, but if your velocity is bigger and that's reversed, then you've got a bigger change in velocity. So that means your rate of change of momentum has increased, and therefore the force has increased. Now if your force increases, clearly your pressure does. Pressure is force over area, so that will increase the pressure. first explanation. Very straightforward, a few logical steps there. Next, because the volume is constant, yeah, constant volume, then L is constant as well. So this L here, that remains constant. But the molecules are moving faster. So therefore they're going to travel across L in a faster time. And that means your time between collisions, T, has decreased. And so the number of collisions per second, it's very important that you appreciate this is per second. You can't just say the number of collisions increases, because if you just keep waiting for long enough, then of course your number of collisions will increase. But this is the rate of collisions, or number of collisions per second, so you should say that. That increases, so delta P by delta T increases, F increases. Again, if your force increases, then the pressure increases, because pressure equals force over area. So that's using kinetic theory to give an explanation as to why this happens. If temperature increases, then pressure increases. All right? Temperature. What temperature tells us is, it tells us about the heat transfer from one region to another region. So what happens is that regions at a higher temperature transfer energy to regions at a lower temperature. Actually, heat transfer is going both ways, but the heat transfer from the higher temperature region is bigger than from the lower temperature region. So there's a net energy transfer. So let's visualise that here. We've got a hot region and a colder region. So the heat transfer from the red zone to the blue zone is bigger than from the blue zone to the red zone. So the net transfer is from here to here. Regions that are equal temperature, there's no net transfer. If they're equal temperature, then the amount of energy going left to right is equal to the amount of energy going right to left. So visualise it like that. They're at the same temperature, so therefore they are still transferring energy, but there's no net transfer in one direction or the other. That's temperature. But now we need to consider temperature scales. As I said earlier, changes in temperature, you can work in degrees C or Kelvin, doesn't really matter. As long as you're consistent, obviously. You don't want to start taking away a Kelvin temperature from a degree C temperature. You can't do that. You can either work purely in degrees C or purely in Kelvin. Temperature in Kelvin is equal to temperature in degrees C plus 273.15. You're not really going to need to worry about the fourth and fifth significant figures there for the majority of your calculations. So 15 degrees C is going to be 288 Kelvin. And here's our two scales. We've got degrees C over here, we've got Kelvin over here. So at 0 degrees C, you're at 273 degrees Kelvin. And the scales, they're just offset. They vary linearly with each other, but they've just been offset. So that means if you go down to here, at 0 Kelvin, you're at minus 273 degrees C. It's just pure addition and subtraction, no division involved. Okay, everyone happy so far? Yeah. States of matter then. Solid, liquid, gas. Okay. What happens as you change phase is you go from close molecular spacing to a little bit further apart to very far apart. Gas. You go from an ordered structure. That ordered structure starts to break down when it turns into a liquid, and then becomes very disordered when it's gas. And the motion goes from vibrational motion to translational. So here you start to transition to translational motion, just slightly. They're just slipping over each other. But here they're moving from one place to another. They're not getting affected until they hit the walls of the container that they're in. Now, melting, what happens during melting is you're going from a solid to a liquid phase, the molecules or the atoms in your material, they gain enough energy to break some of their bonds. Okay, so that's some of the bonds. There's not enough to be completely free of the neighbouring atoms and molecules. The neighbouring atoms and molecules are still exerting some influence on them, and that's why liquid will occupy a volume which is less than its container unless you actually deliberately fill it to the container. So the molecules are still holding it into one object. They become more disordered, the average spacing will increase. Now, they become disordered because that crystalline structure of the solid breaks down. They're still exerting influence over each other, but it's not a nice ordered influence like the crystal structure where you've got everything being pulled in equilibrium and it's a nice equilibrium position. There's no equilibrium positions here that starts to break down, and the average spacing increases. Not a great deal here, okay? There's not a great deal. If you had a block of ice, sorry, not ice is not a good example, but in most cases, in a lot of cases, you have a volume of solid and you melted it in a container, it occupies roughly the same sort of volume. I mean, ice does occupy a little more than water. That's why ice floats. It's more less dense. Sorry, so it's more buoyant. They're free to move around within the bulk of the substance, so they can slip and slide over each other. When you boil something, boiling is, you have to distinguish from evaporation. Boiling is going from the liquid phase into the gas phase, and during boiling what happens is that they break free from their neighbours, so they can move around to occupy the full volume of the container that they're in, pretty much anyway. They're now very far apart, so you see we're very, very far apart, and they're moving freely and rapidly about in a disordered state. As disordered as it can be. So it's that translational motion. They'll actually move across the container, whereas in a solid and liquid they won't necessarily do that. And they certainly won't do it as quickly as in a gas. Evaporation, as I say, evaporation and boiling are different. We've already come across this idea that there's a range of velocities and therefore a range of kinetic energies of the molecules in the bulk of your liquid or substance. So there's, in this bowl of liquid here, there are some molecules that are moving considerably faster than others. They have more kinetic energy. Some of them are going to have enough energy to break free from our liquid. And that's going to allow them to turn into a gas, even though you're not boiling the gas. Sorry, even though you're not boiling the liquid. Okay, so this is a change from liquid to gas before boiling, and it's only a small part of the liquid which is turning into a gas at a time, whereas in boiling, the whole bulk of the liquid is going through the process of turning into a gas. What we're going to do is zoom in on a tiny portion near the surface. Okay, so imagine we could see the molecules, and this one's got more energy. It's moving faster than the rest, so it's able to escape the liquid. That one also very energetic. So a few of them are energetic, and they've been able to escape there, and they form a vapour above the surface of the liquid. So the vapour is the gas form of the liquid. It's possible that some of these vaporized molecules will tend to be moving in this direction and therefore re-enter the liquid. So they kept this as a two-way process. However, there is a net outflow of energetic molecules. Molecules will eventually all escape the liquid if you leave it for long enough, and therefore the whole liquid will evaporate away. Yeah?
Is that temperature dependent? Like evaporation, the rate of evaporation?
The rate of evaporation, yes. So for example, and it also depends on which liquid you have as well, because let's take water. and an alcohol like methanol. Okay? Methanol has a lower boiling point than water, and what that tells you is that it requires less energy to break the bonds in the methanol than in the water. So that applies before you start to boil it as well. And it's easier for the energetic molecules in the methanol to escape than in the water. So I did an experiment where I left, you may have seen the video, it's not a particularly good video, I left a glass of water in the lab over the weekend, and I did a time lapse, so I filmed it, and it took a long time for that to evaporate. It did just a little bit. But I left methanol for a day, and we got about the same amount of evaporation. So yes, it depends on, and it also is warmer as well. So the two things combined, lower boiling point, and the fact that it was warmer, a warmer time of year, meant I got more evaporation from the methanol. So yes, it does depend on that. Yeah, but if you leave it for long enough, it will eventually evaporate away, because it can pick up energy from the surroundings as well, such as the air above it, if it's air above it. So let's talk about internal energy then, and the definition of internal energy. There's some key words that you must always include: sum and random. And those are important because in your body of atoms or molecules, not all the molecules have the same potential energy, nor will have the same kinetic energy. And there's no way to predict the distribution of the potential energies or kinetic energies. So we have to talk about the sum of them, because all of them are important for the combined energy of that system, but also it's randomly distributed, so we have to talk about a random distribution. So internal energy is the sum of the potential energies and kinetic energies, but it's the random distribution of them. And there are two influences on internal energy. If you separate out your molecules, so you increase the separation of them, then the potential energy will increase. There's great potential for the molecules to do work on each other and come back into that bonded structure of either the solid or the liquid. Not that I'm not saying there is a structure to the liquid, but they're still bonded, so there's some kind of structure on the macro level. So potential energy can affect your internal energy, and if the molecules move faster, they have more kinetic energy, so that also can affect your internal energy. Note that, well, we're going to see that rather, this happens during phase changes predominantly, and this happens between phase changes. And you can tell what's happening by temperature changes, because we already saw that temperature is proportional to kinetic energy. So let's have a look at some internal energy changes. If you increase the temperature of a solid, so note there's no phase change here because we're increasing the temperature of a solid. It remains solid throughout this process. We increase the temperature, so that means that the mean Ke will increase. And that, in brackets, because it's a consequence of this point, the atoms, what's happening is the atoms are vibrating with larger amplitudes around their equilibrium position. So a solid is not a static object. Within the solid, you have the molecules or the atoms occupying a region, and they have an equilibrium position. There is a slight potential energy increase. You know that when you warm things up, then they expand. So that does lead to a potential energy increase. It's important to include the word slightly. There's a slight increase in potential energy. But it's not changing state, so there's no major one here. The internal energy has increased because kinetic energy and potential energy have increased. Okay, so that increased the potential, the internal energy, and so did that. So that would be one way in which internal energy can change. Same thing would apply for a liquid as well. What about a solid that melts at constant temperature? So this is a change of phase. The solid melts, turns into a liquid. And the temperature at which this occurs is the melting point of that solid. So if it was ice, then it would be at 0 degrees C or 273 Kelvin. The mean kinetic energy remains constant because the temperature is constant. Remember that E is equal to 302 K2. Potential energy increases because the mean separation of the molecules or the atoms increases. And they also become more disordered, going from solid to liquid. And then, therefore, the internal energy increases just as a result of potential energy increase. Okay. Any questions about those? Excellent. So, last thing, heat capacity. Specific heat capacity, the word specific, by the way, means that you're dealing with a unit mass of something. So this is the amount of heat energy needed per unit mass, that's the specific aspect, to raise the temperature of a substance by unit temperature without changing state. So I put in that this can be in kelvins or degrees C because a change of 2 degrees C is equal to a change of 2 Kelvin. A change of 7.3 Kelvin is the same as a 7.3 degrees C change. The equation is, this is your heat energy, the amount of heat energy, mass, specific heat capacity, and change in temperature. And the units are joules per kilogram per Kelvin. Even though the temperature change can be achieved by degrees C or Kelvin, the unit is Kelvin. So you put the Kelvin in the unit if you need to. You write the unit. The experiment that you would use for measuring the heat capacity of a liquid is shown here. So you have a container here, you've got your liquid, immersion heater, thermometer, ammeter and voltage to measure the amount of current going into your immersion heater, and your voltage that allows you to find the power, and that's your power supply. So I've labelled those things there. And what you would do is you would measure the initial temperature of the liquid. You'd then heat the liquid for a specific amount of time. Using the current and voltage, you can find out the power of the heater. With that combined with the time allows you to work out how much energy you've transferred to the liquid. You find the final temperature after your time has elapsed. And you already know the mass as well, so use weight balance or something to measure the mass. What you can do to make the experiment as good as possible is take into account the fact that some heat energy will be transferred to your container, making sure your container is well insulated. So the container has a specific heat capacity as well, and a mass, so you factor those into your equation. And what you can do is after your time has elapsed, you turn the heater off. You can wait until you measure a maximum temperature. So you keep monitoring the thermometer, and when it stops going up and starts to go down, just before it starts to go down, if you keep monitoring it, you'll know what the maximum temperature was. That would then be the final temperature that you would use, because it's going to take a while for the heat to be dispersed through here, through the liquid, and therefore reach the thermometer. Okay, so that's your heat capacity experiment. The calculation, W equals IV times T. Delta Q then becomes that, rearrange it, so C is IVT over N delta theta. Yeah.
You know, for the container, is it better to have a high specific heat capacity for the container or low specific? Or it doesn't?
I don't think it would matter as long as you factored it into your calculations. But you probably want something that insulates as well as possible, because you don't want it to be transferred into the container. Lots of heat energy transferred into the container and then to the surroundings. So you want to keep it low.
So is it the insulator inside between the water.
Well, no, you can have a container that is not a conductor.
A plastic one.
A plastic one or glass one, yeah. And then surround that with an insulating material. You definitely have to, whatever you use, always surround it with an insulating material. Okay. Excellent. Oh, latent heats, of course, as well. Latent, actually, this word here, latent, means hidden. And the reason that it's called a latent heat or a hidden heat is because when they were doing this experiment in the past, scientists, they noticed the temperature is going up. So yeah, we can understand that. We're putting heat energy in. It's causing the temperature to go up. And then there were these regions on the graph where the line was horizontal. They're still putting energy in. So they're like, well, where's all our energy going if the temperature's not going up? They're expecting the temperature to keep going up, going up, going up, going up. But it didn't. It would go up, go horizontal, go up, go horizontal, and then go up. And it coincides with where it's changing phase. So these are the heat capacities, if you like, for, I don't know if that's quite the right word to say, but these are the equations for where you are dealing with phase changes, the latent heats. Okay, first up, latent heat fusion. That's the amount of heat energy required to convert your material into a solid. And it happens at a constant temperature, and therefore you don't need to have a delta T to it. So it's the mass times the latent heat of fusion for your substance. Then you have a different latent heat for the boiling point, so the vaporization. Latent heat of vaporization, that's converting a unit mass of liquid at its boiling point to gas at the same temperature. Okay? So temperature is constant during a phase change, and that's why there's no temperature changes in those equations. It's easier to visualize if you have a graph, which will come up in a moment. The units of these, no temperature change, so joules per kilogram. This is the graph. So we've got temperature along the y-axis, and this is your heat energy along the x-axis. And these are those horizontal aspects of the graph. So this is during the phase change here from solid to liquid, and this is liquid to gas. So that's your latent heat. This is where they were like scratching their heads thinking, well, where's our energy going? We're putting energy in, but there's no temperature change. And you'll also notice that there are different gradients. So let's just annotate this. That's our melting point. That's our boiling point. If this were ice, water, and water vapour, then 0 degrees C, 100 degrees C. So it's solid here, liquid here, and gas here. So you can see that we have different gradients, can't you? That is deliberate. There's a steeper gradient for the solid and gas than at the liquid phase. And that indicates that each phase has a different specific heat capacity. So you shouldn't assume, unless it's a warranted assumption, because there's no information given to you for different phases, and that the solid, liquid and gas have the same specific heat capacity, because they don't. Liquid, in this case, has the highest specific heat capacity. It requires more energy here to produce the same temperature change. So more energy here is required to produce the same temperature change than when it's solid. So that's what the gradients of the graph tell you. And that is the graph. So, and you can see here as well, you've probably heard me say this before. Let's say I'm going to be very cruel to you, and I'm going to scald you with water at 100 degrees C. Okay, so I'm going to pour some boiling water on you, because I'm nice like that. You're going to get a nasty burn. You already know that. But let's say now I get some steam just over 100 degrees C. It's at 101 degrees C. And if I scald you with that, are you going to get the same burn, a less worse burn, is that right? A burn that's not so bad, or are you going to get a worse burn? Well, what this graph shows you is that, yes, it's only 1 degree hotter in temperature-wise, but actually it's got this much more energy. So it's going to do much worse damage than water at 100 degrees C. So, yeah. It's okay, I'm not going to school you. I'm not actually that cool. Right, that's the content covered for today. I've got a couple of videos to show you. They're quite interesting. These are about gas turbines. And gas turbines, they are one area of engineering where thermodynamics or thermal physics plays a massive role. You're dealing with all sorts of pressure changes and temperature changes. Of course, there's lots of structural engineering and materials engineering. I mean, the way that you get turbine blades that can operate in an environment which is hotter than their melting point is just phenomenal. That is phenomenal engineering. So you have to design materials which can withstand incredible temperatures, and then design something to keep them cool in that environment, which would, even though they have such a high melting point, cause them to melt. So, whenever a gas turbine company, such as Rolls-Royce or General Electric, design a new gas turbine, it has to go through a number of safety tests. I'm going to show you 2 of those tests. The first one is called a blade-off test. So what they do is they have their gas turbine and they blow it up inside, they blow up the blades, and the engine has to be able to keep all of the blades inside itself, because imagine if the blades came off and went into the aircraft, that's going to do lots of damage, so you don't want that. So that's the first test. The second test is a great one. This is the bird ingestion test. So aircraft flying, well, birds fly as well. Now what happens if you fly into birds and they get sucked into the engine? The engine has to be able to cope with a certain amount of bird ingestion. So let's see these videos. This is a blade-off test. So they managed to keep all the blades inside. That's good for the passengers and so on. But there's lots of shaking about that. Next one is the bird ingestion test. That's what it looked like. Quite high speed. And then it'll show you slowed down as well. You see blade 21 takes the brunt of the hit. Did you see the blade flex there? Yeah. Does it hit that? We're talking about seriously big birds here. We're talking like geese that they're testing the engine with. Now when I was at university and I was learning about gas turbines, and they're telling us about the bird ingestion test. And one of the students said, "What, they fire live birds into the engine?" No joke, they asked that. They said, no. They're frozen birds. What, they fire frozen birds into them? No. So obviously they defrost the birds first. So, but anyway, they do have to do bird tests to test that everything is safe. And that's what that will show. Great, okay, so that's it for today. All right.